Today, the topic of our lecture is fatigue loading of helical compression spring and how we will use the ZMLD data for design of helical compression spring. First of all, let's talk about fatigue loading. In fact, before that, let's talk about the dynamic loading and its type. Dynamic loading is a type of load whose magnitude is going to vary with the passage of time. Let's say we have a load P. The magnitude of this load is not constant, then this type of load is called dynamic load. These are different types of dynamic loading. We have discussed these types in previous lectures, but let's discuss it over here as well. I have taken the stress on y-axis and the Engr theta on x-axis. If you see at 0-degree angle, the stress is this in case of fluctuating, and at 90 degree or pi by 2 the stress is this one. Then it decreased like this, and then again it started increasing. So I have taken different points and the stress across these are different. You can see this stress is greater than this one, so the stress is changing. Now let's define each type of load. The fluctuating load is the load where sigma max will not be equal to sigma minimum, and both sigma max and sigma minimum will have positive signs. This is sigma max and this is sigma minimum, both are in positive direction. In case of alternating, this is sigma max, this is sigma minimum, they are not equal to each other, and this one is positive while this one is negative. So this is the definition for the alternating. And for the completely reverse, sigma max will be equal to sigma minimum, and sigma max will be drawn in positive direction while sigma minimum will be drawn in the negative direction. Similarly, for the repeated load, this is sigma minimum, which is equal to 0, and sigma max will have some value in positive direction. Then let's discuss about the variable stress and the mean stress. Variable stress can also be represented by sigma A, called alternating stress, and it is equal to sigma max minus sigma minimum divided by 2, while sigma mean is equal to sigma max plus sigma minimum divided by 2. In case of static, variable stress is equal to 0 because there is no variability in the static load, and sigma mean for it will be equal to the stress applied, or we can also name that stress as sigma max. And in case of these three, fluctuating, alternating and repeated, the sigma variable will be less than sigma max and sigma mean will also be less than sigma max. In case of completely reverse stress cycle or completely reverse load, the sigma variable is equal to sigma max and sigma mean is equal to 0, which is less than sigma max. So I have discussed these things in my previous lectures as well. Now, what is this fatigue loading? The term fatigue means tiredness. So whenever you apply any of these loads and the element upon which these loads are applied gets started to fail, or micro cracks start appearing in that element before the yield point or the ultimate point, then that type of load is called fatigue loading. Talking about fatigue loading, let's discuss fatigue strength as well. Whenever there is a static load, the number of cycle for it can be termed as 0, and for the static load, the strength of that element will be equal to the ultimate strength SU. And if you want to have more number of cycles, or if you want to apply dynamic load upon that element, then the strength of that element will decrease, or in other word, you should apply such a load on that element which will be less than the ultimate strength. So that strength can be named as the fatigue strength, and if you further increase the cycles, it will decrease the fatigue strength like this, and for 10 raised to the power 3 the strength will be this. And finally, so that strength can be termed as endurance limit, represented by SE dash. Now if you design anything in this range, means if you want any number of cycle equal to 10 raised to the power 6 or greater than that, you can use that element for infinite life, but the stress applied on that element should be less than SE dash. But this SE dash is for an ideal case, when the surface finish is ideal, there is no notch. But if you want to have an element that needs to have infinite life and there is a notch, or the surface finish is not good, or you want to use that element under a temperature different than the one for which SE dash is found out, then for that the endurance limit will be represented as SE, and it will be equal to Ka, Kb, Kc, Kd, Ke and Kf multiplied by SE dash. So then you will have to use this formula. Since we have talked about it, let's discuss different Feller criteria for the dynamic load as well. Let's take sigma mean on the x-axis and sigma variable or alternating on the y-axis. And as you know that ductile material will fail for the static load at yield point, and it will fail at endurance limit when there is variability in the load. So when you connect these 2 points, it will give you this line, and here this line shows that if you are at this point, then here if you add the value of sigma mean and this value sigma variable, that will be equal to sigma max, and this should be less than the value of the stress at which the body will fail. So this is Soderberg failure criteria. As you know that line equation is given by x divided by a plus y divided by b is equal to 1, and a is the point where the line will pass through x-axis, and b is the point where the line will pass through the y-axis. So here in this case, x is sigma mean and y is sigma variable, and a is sigma y and b is se. So when you replace these things, it will give you equation that is sigma m divided by sigma y plus sigma v divided by se is equal to 1. So this is the Soderberg equation without factor of safety. Now if you want to be safe, so divide Se and sigma y by a factor of safety, and it will give you this equation then. Now as you know that for brittle material, the element will fail at ultimate point or sigma ut. So join sigma ut with Se, it will give you this line which is called Goodman line, and this is Goodman criteria, means that if you are below this line, your body will be safe. So this is the equation for this line. Since for the brittle materials, instead of sigma y, body fails at sigma u, so when you replace sigma y in the Soderberg equation with sigma u, you will get Goodman equation. So this will be the equation when you want to be safe with the factor of safety for the Goodman criteria. Now let's talk about another criteria, which is Gerber criteria. According to the Gerber, he did many experiment and he came to know that even above this Goodman line, for example this point, the body that he tested was safe, and he through his experiment he came to know that the body will safe under this parabola, and for that parabola he gave this equation. And if you want to be more safe, this will be the Gerber criteria with the factor of safety. Divide this with the factor of safety and this with the factor of safety, and when you simplify you will get this equation. As I told you earlier that sigma mean plus sigma alternating or variable is equal to sigma max. So if you are at this point, means for ductile material, here this sigma variable will be equal to 0, so this sigma mean will be equal to sigma max, which will be equal to sigma y. Then a scientist came and he said that instead of making this sigma a equal to 0, make this sigma m equals to 0, such that sigma a is equal to sigma max, which is in turn equal to sigma y. So this should also be safe. So he take, let's say, this point sigma y, and he drawn a line for it, and he called this line as Engr or yield line, and he said that the body will be safe under this line as well. But as I told you earlier that a premature failure will occur when there is a dynamic loading, and above Se the body will fail. So this, if you see, this region is not safe for the dynamic load, and according to the Goodman, this area is also not safe. So Gerber modified his criteria, and he took this line which was his own line up to this point, and after that he took this Engr line. This was the equation for the Engr line. So the black line shows modified Goodman criteria. He said that now the body will be safe under this region. So this is called modified Goodman criteria, and this can be used for this line, and these two equations which were for the Engr line can be used for this line. So these were the equations for different failure criteria. Now let's take the Goodman line for the understanding purpose. Now you know that in case of the spring, there will be shearing stress in the spring, so this sigma v should be replaced with tau v or tau a, and this sigma mean with the tau mean, and similarly this sigma ut should be replaced with SSU, and it will be replaced with SSE. So this is how the Goodman criteria will be drawn for the spring, and this Goodman equation will also be modified. This will be tau m, this will be tau v or tau a, this will be SSU, and this will be SSE, like this. And Soderberg and Gerber criteria will also be changed similarly. Now after that, these equations, if you want to be more safe, can be written with factor of safety as well, like this. Let's take this point. When you go from this point, you will have to pass through this point to go to this SSE. And you know that at this point, this is the strength of the body of the mean component, and this is the alternating component of the body strength at this point. Let's name these component as SSM and SSA. Now this is where ZMLD data comes in. ZMLD was a scientist. He tested different springs, and he said that material size, tensile strength do not have any effect on the torsion endurance strength when they are 3 by 8 inches diameter. He tested the springs at minimum shearing stress equals to 20 ksi and maximum shearing stress of 90 ksi, and he said that the springs were safe. This data is for unpeened spring. I will talk about peened and unpeened springs later in this lecture. Now what is this tamine? It is the stress in the spring when the spring is coiled or manufactured. When you further load it to the tau max equal to 90 ksi, the ZMLD said that this spring is still safe. So for that, let's find out tau alternating or tau variable, that is equal to tau max 90 minus 20, which is tau minimum, divided by 2. It will give you 35 ksi. And if you want to find out tau mean, you will have plus this 90 with the 20 and divided by 2, it will give you 55. Since the spring was safe at these values of tau a and tau m, so we can say that 35 ksi was the alternating strength component and 55 was the mean strength component of the endurance limit. So represent 35 with SSA and 55 with SSA. Instead of this tau m, write SSM, and instead of tau a, write SSA for the ZMLD data. So these will be the equations. As you know that for the spring, this will be the equations whenever you want to be safe. This is for the Soderberg criteria, this is for Goodman criteria, and this is for the Gerber criteria. Now from the previous slide we have obtained these equations as well. Now when we rearrange these equations for SSE, we will get these equations, and you know this is given by the ZMLD data, and this is also given by the ZMLD data. This is 35 and this is 55. Now if we find out this and this also SSE, we can find out this SSE for Soderberg, this SSE for Goodman, and this is SSE for the Gerber. SSY is equal to 0.45 into SUT, and here SUT can be found from this formula, that is A divided by D to the power n, and the value of A and M can be found from table 10.4, and SSU can be found from this equation, that is equal to 0.67 multiplied by SUT. So using this equation and this equation, we can find out value of SSU and SSY, and when you put these value, means this SSY over here and this SSU in this equation or this equation, we can find out the value of SSE for different criterias. This is where the work of ZMLD data is finished. Then after that we will not use ZMLD data anymore. So we have found this SSE, SSY, SSU. Now if we found out this TA and TM, we can predict what is the factor of safety. So for that, draw a relationship between tau A and tau M and identify the strength points, and then draw the failure criteria. This will be the Soderberg criteria, this will be the Goodman criteria, and this will be the Gerber criteria. Now after that, let's you are inside over here. Let's say if you are over here on this line, you may be safe or may not be safe according to the Gerber, but according to the Goodman and Soderberg, you are not safe. But if you are inside over here, you are safe according to each, and how much you are safe according to each criteria, we can predict it when, let's say, find out this value, that is tau m, and this value tau a, and when you put these values in this equation, it will give you the factor of safety. But there is another way as well. For that, what you will have to do is to draw the line from this origin passing through this point, crossing each criteria like this. And at this point, if you see this as the mean shearing strength value, this will be the alternating shearing strength value for this point or for this line. If you do what? Let's say you take this tau m and this mean shearing strength component, it can be represented by SSM. So SSM divided by tau m, it will give you a value that will be equal to factor of safety. Means you are inside from this point by this amount. This is factor of safety. Similarly, if you take this line and divide this line with this line, it will give you factor of safety, and this line is SSA and this line is tau A. Now this is SA according to Gerber criteria, this is SA according to the Goodman criteria, and this is SA according to the Soderberg criteria. Similarly, this is SM according to Soderberg, this is SM according to the Goodman, and this is SM according to the Gerber criteria. Through this formula you can find out tau A, and this FA is equal to F max minus F minimum divided by 2. Similarly, tau M can be found from this equation, and here Fm is equal to F max plus F minimum divided by 2. And this tau M can be found from this equation as well. And this equation, multiply this over here and divide this over here. It will give you tau M is equal to tau L divided by R.
So this is how you will find out the factor of safety from SSA and SSM.
This SA or SM is not this SA and this SM. Don't confuse it with those used in ZMLD data. ZMLD data is only to find out this SE. Now let's talk about what is short peening. Short peening is actually a process in which small spherical particles are taken, which are known as shots, and they are bombarded on the surface of the spring. Because of that bombardment, compressive residual stresses are produced. That is going to increase the fatigue strength of that spring. Let's say this is a spring, and here let's say this is a small shot. This is tracked on the surface of the spring, and because of that, here a small dent will be produced in the spring, and that will be like a dimple. Let's say this is a dimple. If another shot is also bombarded over here, so it will produce another dent like this, and similarly third one will produce like this, and fourth one will produce like this. But if they are overlapped as well, then what will happen? Let's say these two are overlapped, and then another one is also overlapped, and then another one. So what will happen? It will produce a straight smooth surface. What will happen is that here a plastic deformation will occur in this spring, and due to the plastic deformation, you know about the dislocation moment. The dislocation moment will be resisted, and because of the resistance to the dislocation moment, its strength will be increased, and due to which fatigue strength will also increase for that spring which is peened. So when ZMLD took peened spring and he did experiment on that peened spring, he saw that the tau max that he can produce in the spring was 135. So here in case of peened spring, the tau mean will remain the same. So let's find out tau A, which is equal to 135 minus 20 divided by 2, and that will give you 57.5 ksi, and tau M will give you, which is equal to 135 plus 20 divided by 2, it will give you 77.5. Since these two values, this value and this value, is for factor of safety equals to 1, so we can say that this is the mean strength component of the spring, and this is the alternating strength component. So whatever you did in the previous slides for the unpeened, do the same for the peened the spring. Now after this lecture, I will do different problems as well on this topic. So if you want to further understand this topic, then do watch the upcoming videos on this topic.